Hello friends of maths. We are identifying subsets of the complex plane determined by straight lines, and we're also looking at circles. First thing I'd like to do is to define this idea of locus, loci as a plural. So as you can see, it's defined by a set of points in a plane that satisfies some given condition. So that's your definition of what a locus is. So it follows, all the points follow some condition, or in other words, it's like a path traced out by moving according to some known rule. So all of the points in the set follow the rule. So I think that's by now something you could relate to. So there's a locus. And we're going to use that concept inside identifying subsets of the complex plane. So what we're going to do is look at some examples and some ideas that pertain to straight lines, and then likewise with circles. Now, starting fairly simple. For example, if we have the set of Z such that the real component of Z equals 6, which is a constant, we can express that like so. If we have our complex plane, Argand diagram, and we got the real and imaginary axes labeled as such. Now it's basically saying all the points in this locus are defined by the real component of Z equals 6. So on the real, if we say 6 is here on the real axis, all of the points follow that. So what we end up with is a vertical line. We get a line that's parallel to the imaginary axis that always goes through 6, the real 6. So if we have this locus here, Z is the set of points, of all points that satisfy the condition. The imaginary component of Z is 2 times the real component. We actually have a straight line, and that straight line will have a gradient of 2, and it will go through the origin. So the y-intercept is 0, and so on. It's continuous. So basically that would match any point where, to get the imaginary component, which is going up this way, we have to double the real component. So a Cartesian equivalent to that, a Cartesian equivalent Cartesian equation to that would be, so the equivalence of the imaginary axis is the y-axis if we're talking Cartesian, and we have to double the real. So in equivalence we're doubling x, so y equals 2x will be the same. So y equals 2x, a Cartesian equivalent. Okay, so sometimes we're required to derive the Cartesian equation from the given locus, from the complex plane. Alright, now before we go into more involved ones, we need to review some essentials from junior, some inequalities and how to plot inequalities. Okay, as you can see, we have y equals x plotted, okay, in red, and we can see that that's got a gradient of 1. Its intercept is the origin, and you're very familiar with that. If you're not, you're watching the wrong video. Go watch something else. Now you hopefully can remember the difference between this and the second statement, and the second statement is y is greater than x. So that's a region. Okay, now notice how the line y equals x is not included. It is dotted, so therefore it is not included. Okay, so you need to remember that. And if we change that to y is less than x, it's the same, but the region below is shaded. Now you can always do a test point to check whether you have shaded in the correct region. So if y is less than x, like this one, oh, I've got white ink here, that's pretty much invisible to you. Let me check that. Okay, we'll try again. So we've got y is less than x. Now let's use a test point that's in the region there. So we know that this point here is in the purple region, and it's 2, -2. So x equals 2, and y is -2. So we sub it in. And is -2 less than 2? Yes, that's a true statement. So we've shaded the correct region. Okay, that's all junior stuff, or at least that's year 10 anyway. It's certainly stuff you've done. Now if that's y equals less than x, what's the difference between that and y equals less than or equal to? Is basically the line itself. Okay, so y is less than x doesn't include the line. Y is less than or equal to does include the values where y equals x, hence you have a solid line. Same works for greater than and greater than or equal to. You can see that with greater than or equal to, it's got the solid line. Here we have a circle with radius of 4, center about the origin. Its equation is x squared plus y squared equals 16. You can also plot inequalities to do with circles, and two examples here. This is if 16 is less than x squared plus y squared, or perhaps more usefully writing it in terms of x squared plus y squared. We have, if 16 is less than that, that is greater than 16. So what we have here then, the difference between that and the equation for a circle is that there. So that's x squared plus y squared is greater than 16. You can see that beyond those corresponding values for x and y, the shading occurs, and because it's not an equal to, less than or equal to, it's just less than, we have the dotted lines like we saw with the straight lines. One last example, and if we switch the inequality around the other way, this one's a greater than, but it's a greater than or equal to, so it'll actually be complementary to the one above, which I'll turn off now. Okay, so it'll be x squared plus y squared is less than or equal to 16. Okay, and so you have it within the boundary of the circle. I'm going to do some more, as I promised, more demanding examples here. So sketch and describe the region of the complex plane defined by this locus here. So we have z such that 2 times the real z minus 3 times imaginary z equals constant 6. Now if you like, you could think differently about this, and you could write it, you could think to get 2 lots of the real z, I need to have 3 lots of the imaginary component of z plus 6. Or you could think in terms of the other way around, 3 times the imaginary z equals 2 times the real z minus 6, just rearranging that. So we could think it in terms of that. Or you could just leave it in implicit form, and we can consider that as 2x minus 3y equals 6. But to justify it, this is a bit like thinking it through, but you can probably see the links between Cartesian and the Argand based forms, or the Loki based form. Another way of justifying this that's a bit more solid perhaps is like so, and we know the real z times 2, okay, is 2x, and we know that if y equals imaginary z, if we've got 3 times imaginary z, we've got 3y. Okay, so we've got 2x minus 3y, I'm right on the edge of my page here, equals 6. Okay, That's the Cartesian equation, so in other words it's a straight line. You know how to describe that. So it's a straight line, and it goes through, it's got a y-intercept when x equals 0 and an x-intercept when y equals 0, giving us those 2 points as intercepts. Next we're going to sketch and describe the region corresponding to, here we go, different one here. We've got modulus z minus 2 minus I is less than or equal to 3. So deconstructing the statement, it means that essentially the magnitude of, or the modulus or the distance between any point on the complex number and its center, which is going to be 2 minus I, is always less than or equal to 3. So we actually get a circle from such a thing. If you think about that constant distance away from a point, that becomes the center. So let's put on the center first, which is 2 minus I. And by the way, it's subtraction here because that means the difference between any point z and the center 2 minus I. So we have 2 minus I is the point 2, negative 1, which would be there. So center is 2 minus I, which in Cartesian form is the point 2, negative 1. Just like what we saw with the circles, we have a radius of 3 to consider, 1, 2, 3, and 1, 2, 3, and 1, 2, 3. 1, 2, 3, okay. In fact, I've just noticed that the scaling on this, it's a bit distorted vertically, so I might have to fudge it a little bit so it doesn't look like an ellipse. Okay, so it's going to be a solid line because it's less than or equal to, and it's a circle. If it looks a little bit elliptical, that's purely because of the distortion in the scale of the y, of the im versus the re axes. So, and that means all the points are less than or equal to 3, so we shade inside the circle. And the locus condition says everything has to be at most equal to 3 or less than, as far as its distance away from the center. Okay, so that's what's shaded inside, not outside. Okay, and if you had to do a Cartesian equivalent, whether it's in set notation or not, you don't always have to write your answer in set notation. You could just put the equation, but I'll put full set notation. You could just put the equation down in some questions. So it's, remember, when we got a circle that's not in the center, it's x minus h all squared plus y minus k all squared equals r squared from your previous work. So that's what we're aiming for. So it's x minus 2 all squared plus y plus 1 all squared is less than or equal to 3 squared. So that means the radius is 3. I don't think I'd noted that yet. Okay, so it's all the points x and y, the Cartesian relationship, all the points x and y such that we have x minus 2 all squared plus y plus 1 all squared is at most 3 squared. This one we've got z such that the modulus z minus 2 equals modulus z minus 1 plus I. Okay, what sort of shape is it going to be? So we're not given what shape it is. We have to sketch it. So it could be a straight line or a circle. Okay, so we know z equals x plus yi, z minus 2 magnitude equals z minus 1 plus I modulus. And we've got substitution now, and x plus yi goes in instead of z, minus 2, x plus yi there, minus 1 plus I magnitude. So let's collect the real and imaginary parts now, and we get that there. Applying the definition of magnitude, and we do that to both sides. To get rid of these pesky square root signs, we square both sides and expand. So basically we now have, noting that we're using the perfect squares expansion there, so x squared minus 4x plus 4 plus y squared equals x squared minus 2x plus 1 plus y squared minus 2x plus 1. Time to rearrange. So if we were to rearrange these equal terms on the opposite sides, would eliminate each other, making life a bit easier. And on the left we have negative 4x plus 4. On the right hand side we have negative 4x plus 2. Oh no, we don't. Oops. Oh dear. Okay, that's better. I wrote x there before. It should have been minus 2y. So minus 2x plus 2 minus 2y. So 2y. We need to add 4x to both sides, so now we have 2x on the right hand side. We need to subtract 4, so we have 2y equals 2x take 2, y equals x take 1, and you'd be able to quickly just sketch that one using your knowledge and talk about its features if you had to sketch the Cartesian form. One more. In this last example we've got 3 variations on a theme. Now it's just defined by argument, so argz equals pi on 3 is the first one. So this will create what's called array, R-A-Y, which you may have heard from geometry. And array has a starting point, but then it goes on ad infinitum. Now we'll see if these rays that the starting point, and in this case it's going to be at the origin, the starting point is not included because it's all points that make an angle. In this case the angle is going to be pi on 3. Okay, so it has to be a point from the starting point so that it creates an angle, and the starting point itself is not from the starting point, it's on the starting point, so we always have an open end to it. So we sketch that in there where theta equals pi on 3. Alright, so it's good practice to put an arrow on the end because it doesn't have it has a starting point which is not included, and it has no end point. That's what array is. The next one is a variation on the first one. It involves a translation. Note also that the angle is negative pi on 3. So let's draw arg z equals negative pi on 3 first. So we're going to start with that. And there's that ray there, and again that would have an open start there and at the origin, and basically we have we have z plus 3, Like in a lot of your previous work, this will create a translation to the left 3 units. You've seen that with many things in your previous studies. So what we simply do is just move that to the left 1, 2 and 3, and likewise we've got the ray now going off parallel like that there. Okay, finally now we have argz is less than or equal to pi on 3, and we have an inequality there. So that suggests we're going to be shading a region in. Now in general, if you know your stuff, you'll know that the argument is defined as this. We define it in terms of what's called the principal argument. So in general, for a complex number, now be careful, remember it's exclusive at that end and inclusive at that end. Okay, so between negative pi exclusive and pi inclusive, and we now have here negative pi is less than argz, but here's where the condition kicks in, less than or equal to pi on 3. So let's see what that does now that we've clarified that to our region here. First thing to note is that it does include pi on 3, and the second thing to note is that it does not include pi. So we're going to put dotted boundary there. In terms of arrowheads, I've placed arrowheads on both of those rays, the excluded ray and the included ray, and now we're looking at the region that's shaded. Okay, so it's all of this. You get the idea, and now you're covered.